I'm Daniel Levine, and this is the Bio Report. One of the limitations of small molecule drugs and monoclonal antibodies is the difficulty they face in binding to a large number of proteins that could prove to be critical targets in combating various diseases. Aikium is harnessing the power of artificial intelligence and synthetic biology to create a new class of protein biologics called SeqRs that are designed to bind to disordered regions of proteins that have long been beyond the reach of traditional therapeutics. We spoke to Eswar Iyer, co-founder and CEO of Aikium, about the novel class of SeqR proteins the company is developing, how they bind to targets that traditional medicines can't, and the potential to transform drug development by expanding the world of druggable targets. Eswar, thanks for joining us.
Well, thank you so much, Danny, for having me on this wonderful podcast. It's a pleasure to be speaking on this.
We're going to talk about protein engineering, AI, and how your company, Aikium, is enabling the discovery of a novel class of protein therapies that can bind to targets that monoclonal antibodies can't. Listeners to our sister podcast, Life Sciences DNA, may remember Aikium from a recent episode where we interviewed the company's chief technology officer. We'll have some overlap, but we're going to also touch on issues that we didn't there. I'd like to start, though, with you. You have a doctorate in molecular neuroscience and systems biology. You did postdoctoral work in the lab of George Church before going on to 10x Genomics. You've got 100 patents to your name. Was this a linear progression? Are there connections between these experiences that are not obvious?
Thank you so much for asking that question. And yeah, I guess looking back, as they say, hindsight is 2020. There are a lot of connections that you form over time that plays out in the long run. It was not linear; it was more exponential. But I have to thank the people who helped me with the first patent. It was during my PhD in the first year. I saw a problem and I solved it. And one of my professors told me, Ancha Baranova, that, hey, maybe you should patent this. But then I kind of realized that there is value that can be generated from this. And innovations cannot really see the light of the day unless they're protected in some way. So I think it's been a journey overall and sort of growing over time.
I think of George Church being fairly entrepreneurial. What was that environment like? And is there an energy around pursuing technologies that can be commercialized there?
The lab is a wonderful place. I guess one major differentiator I saw between a bunch of other places is the energy that's there. I think George has been very successful in creating a vibrant, open environment where neurodiversity is highly welcome, and people can think and act independently, and he would sort of really enable that. And in that spirit, it naturally creates a sense of entrepreneurship, which he also really supports. And so that's been a great place. The key lessons are work on hard problems, be nice, think of the world as your collaborator, and try to make a positive impact. I think that's kind of how. Of course, lastly, embrace the power of multiplexing. You cannot speak about George without that.
Well, as you think about what you learned in that environment, are there things you're carrying forward as you create your own culture?
I learned two things primarily that I carry forward. One is the culture is extremely important. It may seem like, it's one of those things that's not quantifiable, But in order to be fearless and innovate, you have to have that environment that supports that fearlessness. And that's something that I strive hard to create at Aikium. And I've sort of witnessed that as part of places that have been very successful. The second is just the inspiration is the cost of the genome sequencing broke the Moore's law. And that really inspired me while I was at George's lab, and George is a big player in this revolution. And thinking about what are the principles that led to that, there are three principles: miniaturization, parallelization, and multiplexing. So if you can do this, you can break the Moore's law. And that was extremely inspirational. So everything that I do since then, I decided that I'll be using these principles. So I carry those forward to the core of everything that I've done.
You most recently were 10x Genomics, which we featured on this podcast in October. This is a company that's providing single-cell sequencing technologies to drug developers. You were developing a new platform there. Did this give you any insight into the drug development process?
10x is a fantastic company building amazingly complex platforms that are almost magic-like to the users, and that's fantastic. Almost it's there in every top pharma has a 10x Genomics. In fact, we open drawers here too in Baker Labs. We have 10x Genomics kits. But I was working on very early stage platform development, figuring out all the details and so on. So it is sort of, I knew it went into drug discovery at some point, but I was not really involved in that. I could envision applications based on my own interests and sort of my own curiosities, but it worked on sort of really laying the foundation for some of these spatial platforms.
How did Aikium come about?
A large part of what has driven me in my career is building these exponential technologies that can make an impact in the greater space. So thinking about that, it was very clear that AI and protein engineering were tectonic forces that were going to shape the space. Some of this comes from reading a lot. Some of this comes from just intuition that you build developing technologies. So really, the first principle was, in order to do something like that, even though I did not know exactly what we will do, the first principle was work with the best people. And in that process, I was very fortunate to find my two co-founders, Shankar, who was also from 10x Genomics, and Venkat Mysore, who was at NVIDIA. And we basically spun Aikium. The inspiration at a high level was to take our knowledge or take our experience of solving really tough problems and focus that on a very large problem that can, enable something very positive. And it became very clear that therapeutics is going to be that space. So that was the inception of Aikium.
Well, specifically within therapeutics, what problem did you see that you thought you could address?
Well, here we read a lot about what is the current state of art in therapeutics, and that was a big point of our process, is understanding the knowledge gap. And what we discovered surprised us, which is all the current modalities of making drugs, antibodies, or small molecules are extremely biased to only half the proteome, in 50% of the proteome. So all the darts we can throw to cure diseases literally hit half the dartboard. And the other half, it's been extremely challenging. And the reason being, they are conformationally flexible. They're really floppy regions of the protein that don't have a stable structure. We realized that there's no universal way to bind or modulate these. So Aikium is building the world's first sequence-specific protein binders, enabling the remaining 50% of the proteome to be accessible to therapeutics. So that's sort of the tough problem we are solving. And to give a more recent context, we have the Nobel Prize in protein engineering. And after that, Nature published the 5 unsolved problems still. And one of them is making binders, precise binders. And the second is the problem of protein conformational flexibility. We think of proteins as pretty stable, but even a small protein with 100 amino acids can have 10 to the power of 100 different structural variations. They move around, they jiggle around, and they have these flexible loops that just wobble in ways that we just can't understand. Even the best-in-class AlphaFold cannot predict how they look. And the challenge is all of the current drug discovery, or a big part of the current drug discovery paradigm, rests on structure-based drug discovery. So you need a structure, and then you do drug discovery. Aikium is trying to shift it to sequence-based drug discovery. You start with just a sequence, and you try to make a drug that targets that region.
And how big a landscape of proteins might be undruggable through a structural approach?
Roughly, we calculated that. So the proteome is annotated by different databases to either be structured or not. So roughly, if you take any protein on average, 50% of that protein would have floppy, flexible, conformationally flexible regions. And on average, across the proteome, that's 50%. So almost all targets that are important will have these floppy, flexible regions, allowing a completely new way of addressing the current, well-known diseases and targets. And there are a lot of targets that have been unreachable to small molecules because small molecules want a pocket to fit in, and floppy proteins don't have pockets. And large molecules are not good at binding them. 90% of antibodies are conformational, biased to conformational structures. So I think it opens up about roughly 50% of the landscape on average of the epitope space.
Aikium's developing a new class of protein therapeutics called SeqR proteins. What are SeqR proteins?
SeqR proteins are proteins that are derived from the human proteome, so they're biologically inspired and not completely AI generated, that can bind the target in a sequence-specific manner. In other words, antibodies, the current state of art of antibodies, usually binds proteins on the structure. They like structural conformations. But what if I could just give you the sequence of amino acids that I need to make a binder for? And what if an algorithm could just make it for you? The analog would be, today when we want to make a PCR primer, we don't think about it. A computer algorithm could make it, and it usually works well. That's because we know the physics of and the chemistry of how these molecules, the ATCG pairing happens. But we really don't have such an analog for proteins. But what if we could have something where just by the sequence, you could make a binder? And that's really what these SeqR proteins are. They're highly programmable proteins that can have drug-like properties and bind to these floppy regions of the proteome in a sequence-specific manner.
Aikium is using AI to generate massive library of candidates and screen them against potential targets. Can you explain the way your platform technology works?
So at first, we take the target sequence for which we need to make binders. Then the AI algorithm, which is trained on a very large number of proprietary datasets and public datasets, evolves a SeqR molecule that binds to the target. It tests anywhere from 10 to the power of 8 to pushing 10 to the power of 11 variants. And once it tests them, it understands which amino acid residues are likely important for binding. Then it recommends a library that we can synthesize, an experimental library. And then we experimentally synthesize these ultra-large DNA libraries. And then we convert them into protein libraries and we screen them. Once we screen these, we screen on the wet lab side 1 trillion molecules with the platform. And these trillion molecules go back, the winners of these go back into the AI algorithm. So at a high level, the platform generates 1 trillion AI designed molecules for a given target that gets experimentally screened. And then the winners go back for further selection and finally into improving the AI model even further.
How precise targeting are you able to get with these? How can you be sure you're targeting a protein that's or that you've developed a SeqR that's specific to the protein you want to target and not hitting another protein that just has the same sequence that you're using?
So one of the advantages of going after using sequence-specific binders is you can pre-select sequences that are relatively unique in the proteome, because we already know the sequences of all the proteins. So we can mine bioinformatically unique signatures. And then we make binders, and the second step is we do positive and negative selection. So we take targets that look similar to our targets that we want to bind, and we select against those. So we get rid of any binders that have some off targets, and then the winners basically go and get selected. We also have some cell-based data where we have added our SeqRs to different GPCRs in a cell line, and we know that they only elicit signal when a certain GPCR is present. When we swap the GPCR out with a different GPCR, then we do not see the signal being elicited. So overall, we think this is a pathway to make highly selective binders.
You're using an AI platform that generates a massive library of candidates for you, as much as 1 trillion. Given that you're binding to a specific sequence, why can't you just reverse engineer these and design a protein with the specific sequence you're looking for?
That's a great question. I think really to put this in context, I'll have to put some numbers here. On average, the binding interface of two proteins when they interact with each other, when they shake hands or interact, that's about 20 to 40 amino acids. So at 20 to 40 points, they may shake hands, they may interact. Those are important for how well they come together. Now, if each of these positions can have, proteins have 20 amino acid letters, but let's say for simplicity, you only screen 10 amino acids at each position. So for position 1, 10 amino acids, position 2, another 10 amino acids, and so on and so forth for let's just say 20 amino acids, which is the least binding interface or one of the lower side. Then you really run into an astronomical number. That is 10 multiplied by 10, 100 multiplied by 10,000, and so that's 10 to the power of 20. You get very soon into astronomical space of binding interfaces. This is part of the reason why it's been extremely challenging to make antibodies for important targets like either transcription factors or GPCRs on ion channels. Everybody knows that 30 to 50% of drugs are made to GPCRs, but it's very hard to make antibodies to them because of some of these limitations. So what Aikium is doing is we need these ultra large screening interfaces to optimize these amino acids that may have been not considered by the traditional technology. The current state of art allows you to say do 10 to the power of 9 screens. So if you just did 9 positions, you would basically max out the current technology. Whereas with Aikium, you can combine AI and wet lab screening, and you can push the boundaries to say 10 to the power of 23, 24 in that realm. So that will offer you much higher precision than any of the current technologies potentially can offer.
Is there a point of diminishing return on the number of proteins you generate and screen? What's the difference between 10 million and 10 billion and 1 trillion?
The difference is just how many binding residues how many different variants of the protein can you select. So in 10 million versus 10 billion, the number of positions that are interacting that you can sort of screen is limited to say, 5, 6, 7, 8 amino acids. But on average, you can have 20 to 40 amino acids that are in the binding interface. So you really need to push to 1 trillion or more to get better interface. So we think that it is, we don't know what the point of diminishing returns is, but we do know based on a lot of structures that we are not, there's a lot more screening capability that's needed to optimize some of these interfaces. Of course, once you learn these in AI, you may be able to better predict them. I guess the second point here is a lot of the AI today is trained on relatively static data. For example, crystal structures, in order to crystallize a protein, you have to crystallize them in sometimes not their most physiological conditions. And further, these conformationally flexible regions are not seen in crystals structures because they don't get crystallized. So there's still a huge dearth on the training on how these molecules look as well. So you really want to weight this large parameter space, learn from it, and create a really smart algorithm.
At what point do you move from conducting experiments in silico to conducting wet lab experiments?
In fact, every in silico experiment is paired with a wet lab experiment. So the way it starts is we get a target, and then the in silico team creates a library of binders by using the proprietary platform. Then it is a library of DNA is designed that is then sent to the wet lab. The wet lab team has a proprietary method for assembling these DNA sequences into an ultra large library. We then QC it using multiple methods, including sequencing. And once it passes the QC, we display it and we perform wet lab experiments. So we have a tube in which 1 trillion molecules live. We can basically do different sorts of selections, and then we iterate on those selections using our proprietary workflow. And then those data sets get sequenced and go back into the training models. So it's an extremely large throughput of data feed that we have. At a high level, perhaps I would add that the moat that we are thinking of, we don't think AI algorithm is going to be our moat. The data and the data generation capability, those will be the bigger moats as we have been seeing in the field.
And what have you done to validate the system?
So we've done a lot of biochemical binding assays to see whether our proteins are binding to these SeqRs. We have done cell-based assays where in the cells, which is kind of a higher bar of proof. So we have cells, human cells, that express the GPCR of interest. And then we add our SeqR molecules that are designed to these variants. And then we ask whether there is any cell-based activity or not. These are usually fluorescent reporter-based activities that are triggered by that GPCR getting activated or not. And we notice that we get a pretty decent amount of hits when we send this. So that's kind of the higher bar of proof we have, in addition to a lot of other experiments. And we have a lot more ongoing currently to validate these.
I'm curious what challenges you've encountered in trying to do drug discovery with AI. Have there been problems you've had to contend with?
Building out the platform from scratch at a time when no one wants to, or there's less interest for funding platforms, was a challenge, but we have sort of successfully overcome that. We've sort of built the platform in different ways. And then perhaps having the right assays in place and sort of bringing the expertise in-house. So it's really how you scale, how fast you scale, and sometimes having the right disease models, the right GPCRs, and all of those. These are all subtle things, but they add up in terms of the challenges. But overall, it's been pretty promising and productive, and I think we are sort of hitting our stride now.
Given the broad applicability of the technology and the fact that you're opening up a huge landscape of potential targets, what are you doing to prioritize the indications you'll pursue?
So we are prioritizing indications where the targets that are involved have extracellular regions that are disordered, perhaps are too short for antibodies to be made, and perhaps have decent biology proof, where we're trying to minimize some of the biology risk upfront. But there are, of course, targets that some of our partners want us to work on where they would take some of the risk on doing this. So that's kind of how we are prioritizing the indication space. So these are spaces with broad indications in the oncology, inflammation, and immunology space that can that would be hard for an antibody to go after based on some first principles.
And what exactly is the business model? Is the plan to build your own pipeline? Is it to build the business around partnering?
The plan is we have to strategically execute this. The plan is to have a number of partnerships that can potentially bring in non-dilutive revenue and bring in the expertise needed for Aikium to sort of succeed. But the intention is to take at least a few candidates to development nomination stage. The larger ambition that we have for, say, a 10-year or 15-year is it possible for us to create a platform that can create 100 therapies? Perhaps it sounds ridiculous and perhaps even absurd, but one of the inspirations that I draw from is the fastest therapy that has ever been created. It was an oligonucleotide therapy for a single patient for a rare disease, and that happened within a year. And that happened to a great extent because oligonucleotide technology is a well-known platform. We understand the safety profiles, the basic biophysics is worked out on how to pair these, and the mechanism is worked out. We don't really have an analog for proteins yet. What if you could create a molecule or a class of molecules that would have the safety profile of antibody-like properties, but could go after something antibodies don't and have the programmability of going after any target, almost like CRISPR for proteins? What would that do? Then somebody sitting in their lab could be going after a rare disease at a entry barrier point that's much lower and start testing the assays and generate the data. That's kind of our vision to really have impact in the larger scenario. Having personally taken lessons from the CRISPR revolution, next-gen sequencing revolution, I think there is an opportunity here to make a difference. That's going to be long run for the next 10 years or so. But in the short run, work with partners, take 2 candidates to development nomination, and take the first molecule to clinic. And that's going to build a huge sort of proof point for Aikium.
It strikes me that the challenge with any platform technology that's as powerful as this is potentially is that even though you can generate very promising molecules, clinical development still remains very expensive and time consuming. So how much of a rate limiting step do you think that's going to be?
That's a great question. That is one of the biggest risks for any drug to be developed. And in part, that is why we are trying to find that we are working with KOLs and partners where we can diversify some of that risk. Some of these targets have come from the KOLs that we work with and the partners that we work with. And these are targets where standard approaches like antibodies have failed. And so that's a place where we can make SeqRs and our partners can validate them and test them and take them to the next stage. And we can sort of co-develop it in some way. And then there are molecules that we can strategically develop in-house. So it's a very valid and fair point. And it is a major bottleneck. I do think that it is getting better with how commoditized some of these are becoming. For example, almost anybody can make an antibody for a well-known target or structure of sorts. And that's great to see that sort of commoditization. So then the question becomes, if anybody can make an antibody to a target, then what is limiting? What's the big risk? The risk is going to be biology-based to a great extent, which is very hard to predict. And then the target discovery lags behind the antibody discovery significantly. So if you have new targets or new epitopes you want to go after, a technology that can access those epitopes is really going to win out if you can fundamentally work from first principles. That's kind of how we are operating. So it's going to be a slow, patient, and very strategic play. But we have to be super focused on the first program that goes into the clinic.
These are early days for Aikium. You're at the Baker Bioingenuity Hub at UC Berkeley. How is Aikium funded to date, and what's the plan for raising additional capital?
Yeah, these are relatively early days. We've been in existence for about 2 years, and we are at the Baker Bioingenuity Hub. It's a fantastic place. I think it's a really vibrant place, managed extremely well by Gino and the operations team. So we really enjoy being here. And a big part of, perhaps I'll say, is the really cordial environment, the culture that's been developed here, where even with so many startups, everybody works synchronously rather than asynchronously. That is a very major plus point here at UC Berkeley. So I really congratulate the team for enabling such a place here. Aikium has been funded by several VCs and angels so far. Some are very prominent angels. And so we sort of have a decent runway and a strong support from our supporters. And we are now planning to raise our next larger round. So it's a constant milestone, and we have to hit certain milestones. It's very clear what we need to do. And we're basically putting our head down and going to execute on it. In the long run, really, it's the execution that's going to speak for itself. I think we have executed in a pretty sort of lean manner so far. And I think we're going to sort of use that execution skills to sort of raise additional funds and sort of continue executing the way we've been executing.
Eswar Iyer, co-founder and CEO of Aikium. Eswar, thanks so much for your time today.
Thank you so much, Danny. It was a pleasure, and it was great. And that's great that I could, convey this to the viewers. Thank you.
Thanks for listening. The Bio Report is a production of the Levine Media Group. To automatically download this podcast each week, subscribe to our RSS feed or through iTunes or other podcast manager. To join our mailing list, go to levinemediagroup.com. We'd love to hear from you. If you want to drop us a line or are interested in sponsoring this podcast, send email to danny@levinemediagroup.com. Special thanks to Jonah Levine, who composed our theme music, and the Jonah Levine Collective, which performs it.